Okay, so let's talk. We're going to continue our discussion about conic sections and how conic sections were useful for doing various things. We're going to also return to Apollonius and conic sections later. Some people are going to be talking about Apollonius. Is there anyone here in the room who's going to be doing Apollonius? No, they're all out in the wide world. Okay. So, because it's all kind of rhetorical geometry, conic sections can sometimes be a little bit off-putting. You know, this whole thing of how using their symptoms to do things. And we'll see in today's lecture some examples of how you would use those symptoms. And so if you remember, the symptoms are things like you've got a square on the ordinate equals some rectangle where one length is the abscissa. Okay, and so you've got this quadratic relationship, and the usual way that really the only ways that I know of that can arise if you're constructing it is going to come from similar triangles, because remember, if you've got similar triangles, if you cross multiply, that gives you some sort of quadratic relationship. And of course, the other way is using the Pythagorean theorem, because that's a quadratic relationship. So let's have a look at Abu Sal's analysis of the heptagon. So remember, in the last class, we talked about how Archimedes had done this, this way of constructing a heptagon using a nuesis, where you've got this thing where you want two triangles to have the same area, and all looked rather mysterious. And then Abu Sal came along, I think he was like in the 11th century, and he's an interesting story. Like I said before, he started off as a juggler in the marketplace. He used to juggle glass bottles, and he was very interested in centers of mass, and so he started reading. Archimedes has a famous work on centers of mass, and he read this, and he actually did some commentary on it, and then later he read further things of Archimedes and made more commentary on it, and this is kind of like his crowning jewel, his analysis. So by analysis, I'm talking about this classical Greek way of proving something, which is analysis and synthesis. So what you would do is you would start off with your conclusion, and you would break it down to its parts, and then you would do the synthesis, is where you go backwards. You go from the givens then to the conclusion. And that's, the synthesis is what we typically think of as a proof. But for the Greeks, it was only the second half of the proof. So let's have a look at the analysis. So what you're doing is you're starting off with the heptagon, and you want to break it down into its constituent pieces. So here's a heptagon right here, 7 sides. We can have it inside a circle. That's no problem, right? Because we just do the lines from the vertices to the midpoints of the opposite side, and that's going to give us a diameter. And once we have a diameter, we're going to have the circle. Okay, and so this is actually from Archimedes. Archimedes saw that there was this really interesting triangle that you can construct from the heptagon. And it's a 4-2-1 triangle. So let me explain what we mean by that. So what we're going to do is we're going to take 3 vertices of the 7 vertices for the heptagon, and we're going to make a triangle from it. And the interesting thing about the angles of this triangle, they're in the ratio 4-to-1. Okay, and this follows from a proposition of Euclid from book 6. Is anyone here talk about that? That might have been Carl. That says that if you have a triangle within a certain a triangle circumscribed inside a circle, then the angles are in the same proportion as the arcs they subtend. So here, for example, this arc AG, okay, that is 4/7 of the circle. So that arc subtends 4/7 of the circle. So this angle here must be 4/7 of the angle in the triangle. This is 2/7, so this is 2/7 of the angle, and this is 1/7, so this is 1. So we've got a triangle here where the ratio is 4 to 2 to 1. Okay. Okay, that's just what it is. Now, what Archimedes did next was a really cool thing. So this is where he was kind of like super bright. He went from an angle, from this triangle, he went to a line segment with really interesting properties. So what he did, what you do is you take the triangle that you get from the heptagon here, and you lie it down on its short base here, and you extend that short side in the direction E and D. And what you want BE to be the same length as AB, and you want GD to be the same length as AG. Okay, so what we've done, we've taken our 4, 2, 1 triangle, and we've put two isosceles triangles on either side to make it into one big triangle. Okay, so let's start figuring out what the angles in our triangle are, and it's not very hard. Okay, so for one thing, sorry, I did this in paint, so I hope this is legible. So a dot is 1/7 of a triangle, so it's 1/7 of 180 degrees. So here we have a straight line, which also has 180 degrees, has the same angle as a triangle, right? So if this is 4/7 of a triangle, this has to be 3/7 of a triangle. And if this is 2/7 of a triangle, this is 5/7 of a triangle. You all good? Okay. Now we've got to figure out these triangles here, these angles here, and why can we do that? 7, and they're isosceles triangles. So these angles have to be equal. Okay, so if there's 3 dots here, there has to be 4 dots here, has to be split up evenly. So there's 2 dots here, 5 dots here, there has to be 7 dots total, so there's 1 dot right there. Okay, so the first thing we see is that we've got a whole bunch of similar triangles. Okay, remember we started off with a 4, 2, 1 triangle. Well, here is a 4, 2, 1 triangle. So this triangle ABG has to be similar to, sorry, that should be DEA. Oh, no, sorry. I did mean DBA, because this is also a 4, 2, 1 triangle. So DBA is a similar triangle. And AEB is a 3, 2, 2 triangle. So is AGE. So we've got a bunch of similar triangles. And once we have similar triangles, that means that the ratios of their sides have to be equal. So from ABG and DBA, that means that DB over AB is the same as AB over AG, because we're looking at the sides opposite the 2 angle over the side opposite the 1 angle. So the side opposite the 2 angle is AB over BG, it's there. It has to be the same as a similar thing for the bigger triangle. And similarly for these two isosceles triangle AEB and GEA have to be also similar. So we get a bunch of ratio of sides being equal. Okay, now what we want to do next then is put everything in terms of this line segment EBGD. So instead of AB, let's talk about BE, because AB and BE are the same length. And instead of AE, well, that's going to be the same as AG, right? Because that's an isosceles triangle there. But AG is the same as GD. And so then we can turn these expressions here solely in terms of intervals on the segment. So we get DB on BE equals BE on BG, and GE on GD is the same as GD on BE. And then we cross multiply and we get our second reduction. We've gone from a triangle, this triangle here, and we've constructed a line segment here that has these properties. Okay. Now, at this point, this is where Archimedes before had come up with his nuesis, where he had those two triangles being the same area. That's how he sort of constructed the segment to do this. What Abu Sal did was he looked at this and he thought conic sections, right? So what we want to do is we want to come up with conic sections where GD is going to be an ordinate, yes, BE is going to be an ordinate, and one of these things is going to be an abscissa. Now, Archimedes could have done this because there's a famous problem that he did on the sphere and the cylinder, where he looked at the problem where you have a sphere and you have the problem that we want to cut the sphere into such a way that this volume to this volume is some given ratio. That this is going to be A to B sort of thing. Okay. Now, if you think about this, this would be a straightforward Calc 2 problem, right? Because what you'd do is this would be some integral. You'd use Cavaliere's principle, and you know, you'd have r squared minus 1, something like times pi between x and 1, where you make the cut, and this is going to be equal a on b pi. If this is x to 1, this is going to be minus 1 to x dr. Something like that. And you see that you're going to get a cubic, whatever the details are, hopefully you can see you're going to get a cubic equation. Right, because when you take the integral of this, the integral of r squared is r cubed on 3, and when you plug the x in, you're going to get an x cubed. You're going to go here, and when the dust clears, you get some cubic equation that you want to solve. Okay, and so Archimedes didn't really know how to solve a cubic. What he did was he used two conic sections to intersect it to find the root of this cubic equation. Okay, and Abu Sal saw this, and he used this as an inspiration to do his proof. Okay, so let's have a look what he did. Okay, so in the final reduction, the final piece of the analysis, you want to go from the divided line segment to two conic sections. Okay, so you've got our line segment, which has the desired properties. You draw ABZ, so it's perpendicular to EBGD, and such that AB equals BG and GD equals BZ. And then you complete this rectangle here. Okay, and so then you put in a parabola with vertex at A. AZ is its axis, so it's a parabola sort of going like this. And you've got to do the latus rectum, BG. Okay, so remember what that means. If you have a parabola, that means that BG times the abscissa equals the ordinate squared. And that's kind of like, maybe we'd think of this as y, so we've got a constant times y equals x squared. Okay, now the claim is that this parabola will pass through the point T. Let's double check that. Okay, so if the parabola passes through here, well, if this is the axis, and if that's a point here, TZ is going to be the ordinate, and AZ is going to be the abscissa. And TZ, right, TZ is equal to BE, right? So remember, this is the condition that comes from the line segment. That's the given. Okay, and so we can replace, what can we replace? We can replace BE by TZ and DB by AZ. Right, and so there's the ordinate and there's the abscissa. And so that this given requirement is the same as the requirement that T lies on the parabola, because it satisfies this expression right here. Okay, so that means we have this parabola is A here, and it goes through the point T. Now, the other condition means that it lies on hyperbola with a vertex at B, axis BE, and remember, hyperbolas need two parameters. They need the latus rectum and they need the latus traversum. So we're going to let BG be the same for that. Okay, so here is B. And so the hyperbola kind of looks like that. The claim is that T also lies on that hyperbola. And it's going to lie on that hyperbola if, so what is it? The ordinate square equals something like the latus rectum times the abscissa plus it's kind of like the ratio of the latus rectum to the latus traversum times the abscissa squared, I believe. And that's exactly what happens here, since our given expression GE times BE equals GD squared means that GE times BE equals ET squared, because I'm saying GD equals ET. Is that obvious? Yes, GD equals BZ, but this is a rectangle, so that also equals ET. Okay, so the given relationship means that we have that, and if we go ahead and look at the definition of a hyperbola, right, we get that GE times BE, well, GE equals BG times BE, and that BE is the, what's the BE? BE, I believe, is the abscissa, and ET is the ordinate. And so that relationship there is exactly what it means to be a hyperbola.
Dr. Ryan,
Mm-hmm.
what's the point of putting BG over BG into that final equation?
Because remember in the problem of excess, the excess is an excessive rectangle whose ratio is the latus rectum to the latus traversum. And so BG being those two parameters, we look at their ratio and it's 1. So you get that just that. Whew. So that's pretty cool. And so then, so your homework question then is to do the synthesis, which is to work backwards. And so the synthesis, you've got to be careful. You've got to state what you're given. And then you go through a construction saying what you do in what order, basically the reverse order there. And when you do things, you've got to give a little justification of why it's so. You don't have to give a full proof because we've already done this. You just say, we can do this because by the property of the hyperbola, this is true. Okay, and then at the end, you have your conclusion, and your conclusion should be the heptagon. Okay, but the interesting thing for us, I think, is to see that how using the properties of similar triangles, you came up with a relationship which gives you a conic section. Okay. I am recording, have I? Yes, I am. Okay. Okay. Oops, I shouldn't have done that. No, I'm pressing the wrong thing. Okay, so the other thing I wanted to talk today about was construction of conic sections. And so this will also give us an example to show how you can use Pythagorean theorem to come up with conic sections. Now, conic sections were kind of important to instrument makers. What can you do with a conic section? Well, one of the things you can do is make, if you have a parabola, you can use them to help make parabolic mirrors, which are, you know, kind of like a burning mirror. Has anyone ever seen that Mythbuster about where they saw whether you could actually burn a ship with a yeah. So there's like controversy whether you can actually do that or not. Some people say you can and some people say you can't, but it's kind of fun. The main thing that hyperbolas are used are in the construction of sundials. So you all know the sundial in front of Magruder. And so if you look at the concrete there, that actually should be a hyperbola. Because if you have a gnomon and you have the sun, what is the path of the tip of the shadow going to be? Well, it's a problem of a conic section, right? Because you've got the sun, you can think of the sun as the cone. The sun is the vertex of the cone, it's shining, and like the Earth's surface is then a plane that cuts the conic section. And the path that it's going to get then is going to be a hyperbola. Okay, and so for example, this is some illustration from a 15th century Egyptian treatise on sundials made by a man called Al-Kawandisi, and he was interested in sundials because he's a muwakit, which is someone who calls prayer time. So he had to know exactly when to call prayer. So he was all, you know, he was all about the sundial knowing exactly when was the correct time that he could then call the faithful to prayer. And so I believe this is the sundial for Cairo. So it depends upon kind of the latitude, what the sundial will look like. And this is a generic sundial, and sort of explaining how to make it. Okay, so that means there was actually lots of treatises. It's kind of like a basic geometric problem of how you would construct a conic section. Now there's a problem in that you can't really define the whole curve by straight line and compass, right? Because it's a nuesis, it's a moving geometry. But what you can do is you can plot a lot of points by straight edge and compass, and then you just do the standard thing that how all curves are generated on a computer, or how you can generate by hand, is you plot enough points and then you draw the plots together in a sort of in line, in a smooth kind of way. Okay. So this is how, so Ibrahim bin Sinan wrote a treatise on how to construct the three conic sections. He wrote this around 946. And supposedly he was inspired to do this because his grandfather was Tabit bin Qura, who's a famous mathematician, but his methods of constructing conic sections were criticized as being too complicated. And so he felt like he had to clear the family honor by coming up with his own methods. And his methods are actually really nice and kind of clean. Okay, so you get a line AB and you have this fixed segment AB. And so what we're going to do is we're going to construct a parabola with vertex at B, axis BG, and AB is going to be the latus rectum. So this is whatever you need. Whenever you do a parabola, you need to say, for us, we would just put down an equation, you know, y equals ax squared plus bx plus c. We would need to put those things. for them, as a geometrical problem, you have to put out where you're placing it, how you're aligning it, so that's the axis, and what the latus rectum, what the parameter is. Okay, so once you do that, you then construct a perpendicular BE to AB. And then you pick some point H on BG, and you draw a semicircle at there. Actually, probably what you really do is you get your compass and you just choose a radius and you use a semicircle to find H, but whatever, you do that. Okay, so the semicircle is then going to intersect that line BE at some point T, and then we just complete the rectangle HBTK. Okay, now remember from the homework problem, we know that AB times BH equals TB squared. That's from finding square roots. And we remember that that follows directly from the Pythagorean, applying the Pythagorean theorem to a whole bunch of little right-angled triangles in there. But TB is equal to KH. So we've got AB times BH equals HK squared. So K lies on our desired parabola, right? Because HK is going to be the ordinate, and BH is going to be the abscissa, and AB is going to be the latus rectum. And you just keep on doing that. You just choose more points, DZ, etc. You put the semicircles in, you complete the rectangles, and you're going to get a whole bunch of points B, K, L, M, which are going to lie on the parabola. And then you just extend these ordinates down here such that that equals that. And it's going to give you then K prime, L prime, and M prime down here. And so that gives you a whole bunch of points that are on the parabola. And then in your best hand, you try and smoothly join them. And that's how you make a parabola. So it's a nice little way to do that. He does a similar thing for the hyperbola. So you have a fixed segment AB, and you prolong the diameter in the direction of B, and you put in a semicircle. And so now we're going to make a hyperbola with vertex B. This line here is going to be a diameter. Notice I'm not saying an axis, it's a diameter. So remember, a diameter is just something which cuts chords into two ordinates, into two midpoints. The latus rectum is equal to the latus traversum equals AB. You'll notice that actually whenever you have a problem to do with a hyperbola, you always have the latus rectum equal the latus traversum. Even though you can do it in general for any kind of ratio, I've only ever seen them have the same parameter. And the angles, the ordinates we'll make with the diameter is some given angle theta. So in this thing here, you're given some angle, right? Typically, we do things with 90 degrees, but with this, we can say we're actually given some angle, and we're going to have that angle be theta, and that's the angles the ordinate's going to make with the diameter. Remember that angle, for it to be an axis, that angle has to be 90 degrees, but it doesn't have to be 90 degrees. Okay, so what you do then is you put you pick a point G on the semicircle and you put in its tangent. So that's something that you can do by straight edge and compass. And then that tangent is going to hit the extended diameter at some point Z. And then at Z, you put your ordinate with your given angles theta, because you can transfer angles, and you let this length ZK equal GZ. Okay, and so then the claim is then that K lies on the hyperbola. Okay.
Is it just a coincidence that GZK looks like a right angle?
Yes.
Okay.
Yes. Because this theta is going to equal this theta here. So this is just going to be 180 minus 2 theta.
Okay.
So this angle can be anything arbitrary. And this follows from the property of tangents. Let me just. It's kind of very similar to the property that we used. So this is another way that we could have done square roots. Because if we have so what does it mean to be a tangent? Well, that means that this angle here is going to be 90 degrees. So the angle that a tangent makes with the radius is 90 degrees. So we can do Pythagoras' theorem on this. So this is B. So we have, this is some R, so the radius. So we have R squared plus GZ squared equals R plus BZ squared. That follows from Pythagoras' theorem. If we just multiply this out, this is R squared plus 2RBZ plus BZ squared. R squareds cancelled. 2R is a diameter, and so the diameter is AB. So we factor out a BZ. AB plus BZ is AZ. So that's where we get that from. But GZ is exactly equal to ZK. That's how we defined it. And so that's why K lies on our desired hyperbola. Because now this is the ordinate and this is the abscissa. And that relationship there tells us exactly what we need. Okay, so that's how we generate one point on the hyperbola. And then we do the same thing with different points on the circle. We take their tangents. They're going to intercept the extended diameter at IT and other points. We then draw lines parallel to our first line, because then that will have the same angle theta, and IM is going to equal IH, and TL is going to equal DT. And so those points B, M, L, K all going to lie on the hyperbola. And then to do the other half of the hyperbola, you do the same thing. We take KZ, and since it's an ordinate, that means it's half a chord. So then we just extend it at the same length as that to some K prime. And so we're going to end up with our branch of the hyperbola. So B is the vertex for the diameter. It's not the vertex for the section. And that's, there we go. Okay, and so again, that's kind of neat. And it just kind of illustrates how you can use the standard quadratic relationships in geometry to construct these conic sections. Okay, so that's enough about conic sections for a little bit until we talk about them. I don't know if it's next week or the week after. Someone's going to talk about Apollonius.